Okay, so what I've done is I've set the interferometer measurement display up that we had before, and I've connected it up to the laser head as before. So this will shoot a light beam down the bench to a plane mirror that I've got set up here, and I'm just using a little bit of paper and a bit of old circuit board under there to get the alignment right. And I'll show you in a minute when we turn it on that now shoots just off a plain front surface aluminium mirror. It's shooting that beam back into the left detection window here. Okay, so using the controls on the front of this, we can use this to aim the target, to line up the beam. So what the purpose of this test is twofold. First of all, I want to see whether or not I can get the reset light to go out. And it'll go out when I get correct beam alignment. So provided this beam alignment meter swings over far enough here and stays there, the system will reset. Now what that's doing is it's simply picking up, with the electronics that are in the head, it's picking up from a photodetector that's behind this little window off to one side. It's picking up the light level and it says, have I got enough there to give me a valid signal, yes or no? And if there's enough light intensity there, the beam alignment meter will be over in the green, and that'll enable us to reset the system. So that's the first test we're going to do. The second one is a little more involved. This is the cable that runs between the laser head and the measurement display unit. What I've done here is I've actually put into circuit a 25 pin parallel breakout board, so that I can monitor all of the signals that are on this line. So I've got a meter and I've gone through the charts and worked out what each pin of these correlates to in terms of its meaning for the system. And there's one particular one that I'm looking for, and that's the reference signal. Now, although we haven't got any optics in the beam path here other than a plain mirror, we're not going to be able to count interference fringes. But that's not entirely correct, because inside the laser head, it has its own interferometer. It actually has a beam splitter and some photodetectors and some polarizing filters that perform all the same function. The reason it does that is it takes the two frequencies that are coming out of the laser tube and it puts it through its own internal interferometer to create what's called a reference signal. And it uses the reference signal as the base. It then looks at, through this detection window, it actually looks at what's coming in on the other channel, which is the channel that's been interfered with by the moving optics on your measurement path. So without overcomplicating this too much, what I want to do first of all is to power it up, make sure that we've got accurate alignment of the beam to this little target that's here, and once we've got that, we want to see if we can check the reset. Okay, so we'll turn it on, and as before, it all comes up, and after a few seconds we should see that reset light start to flash. There she goes. Okay, now we'll check that we've actually got a beam. Can you see there? The beam is actually on the target. Let's just adjust that a tiny little bit. There we go. It's very, very tricky to get it spot on, but that's pretty close. So what we can do now is we can turn it around so that the beam is just disappearing in onto the main photodetector there. At this stage, the system doesn't know or care whether the return beam has been moved or interfered with or anything else. So the first thing we see is that the beam alignment meter now is well over in the green, and if we press the reset button, it goes out and stays out. What we've got now is we've got a little bit of flickering happening up here on the display. Now if we press smooth, we see the flickering stop, and if we go to the times 10, we can actually see that it's trying to count sort of something. That's in reality meaningless garbage. That's not really actually measuring anything, because we're not causing what's called a Doppler shift of the return beam. Okay, so I'll just pause it there for a sec and I'll go on to the next bit. Okay, so this is the setup now. If you can see over there in the corner, we can see we've got the breakout board, and I've got the scope set up on a completely different range of settings now, because we're now looking for something that's a whole lot faster. The interference pattern that we're looking for is going to be running at 2.5 megahertz. So inside the laser head here we have actually two laser light beams being produced at very slightly different frequencies. Now if you tried to pick up the actual wave of light, because light travels so fast and because the wavelength is so short, it's only 632 nanometers for the helium neon laser, to try and pick up that wave just with a normal photodetector and to try and measure it, it's going to be in the hundreds of terahertz, which is like so fast that there's no equipment around that will measure it. But an interesting quirk of the way this laser works, it's got a special magnet around it, a circular magnet, which actually splits the primary laser beam into two beams that are about 2.5 megahertz apart if it's running properly. So one of the main things we're looking for to make sure that the laser's working and that all the detection electronics are working is a 2.5 meg square wave on the reference signal here. Now we should also be able to pick it up on the measured signal on the return beam. Okay, so let's go looking. If we go here to pin number 5, what we can see here is a wave that, well, it's not quite a square wave, but it's pretty darn close. And you know, as electronics age, the capacitors get a bit dodgy, and if you look at this wave in the manual, it's a perfectly symmetrical, perfect square wave. But there's a couple of interesting things. Firstly, the amplitude. We're on 0.1 volts per division, and this is 2.5 of those, which means it's 0.25 volts. So it's quite a weak signal, but it's correct. According to the manual, it should only be 1/4 of a volt. It's not a perfect symmetrical square wave, but it probably won't matter. What I'm most interested in is what's the frequency of that wave. So if we go peak to peak, I'll just move it over just a little bit to one side so we can get the beam to align right on that point there. So you can see it right at that point. It's exactly 2 divisions, and we're running a time base here of 0.2 microseconds. Okay, so if you work that out, 0.2 times 2 is 0.4 microseconds, which works out to 2.5 million cycles per second, which is exactly 2.5 megahertz. If we go on to the return beam, we'll see here now that this is the return beam on one of them and the return beam on the other channel. So the reference signals on pins 4 and 5 here are exactly 2.5 meg, and the return beams are at 2.5 meg. So one of these waves, one of these square waves, will shift slightly when we put a polarizing beam splitter and a reflector in the beam path and return the interfered beam back through the interferometer that's in here. We're basically going to superimpose the reference signal onto the shifted signal, and the difference will be what we're measuring. So it creates this using its own internal interferometer. So this is a 2.5 meg reference signal, and then we can move over to one of the shifted signals on the other channel, and that's what's coming back. So a couple of things we're going to try and do. Can you see the... just move that around so you can see the display. The first thing I want to test is if we interrupt the display, what happens to the ready light. The reset light should go off, okay? Should start flashing because it's lost its beam alignment. So even though the beam alignment's come back up, when we interrupt the beam, the beam alignment drops to 0. Okay? So interrupting the beam causes it to lose its alignment. We reset once it gets its alignment back, the system resets itself. The counter goes back to 0 and the reset light stops flashing. Okay? So all of that seems to work. What happens now to the reference signal? When we interrupt the beam, the reference signal should stay constant because that's what it's for. And it's generated internally. So interrupting the beam doesn't change the reference signal. Okay? But it does bring up the ready light because it's the reset light because it's lost its beam alignment. So we'll reset the system. And now let's have a look at the return channel. So this is what the manual and all the other documentation refers to as the Doppler signal, which is the shifted signal or the signal that's coming back from the measurement optics. Let's interrupt it and see what happens. Well, what we should see here, if this thing's telling us the truth, this should just go to garbage, which it does. You see it, extremely high frequency signal there. It's just meaningless because there's no interference of the light waves. Okay? So what you're seeing there is probably the primary signal because you interfere in the path. So all you're going to see is just those really, really super high frequency signal that this poor little scope at 60 mag isn't going to ever keep up with. So we reset and we'll go back on our reference signal again, which we can see is exactly at 2.5 meg and 0.25 millivolts. Oh, sorry, 250 millivolts, which is correct. So while I was at it, I got the meter out. I got my voltmeter out and I checked the voltages on here according to the good book, and everything is right. We've got exactly 15 volts plus and minus. We've got exactly 5 volts within a millivolt or two. So the controls in there are working really nicely. So that's it. We're ready to start shopping for some optical elements. Some beam benders, which are basically a 45-degree mirror, or a 90-degree mirror if you like. That's just a mirror at 45 degrees that'll put the beam around a right angle. We need a polarising beam splitter, a thing that Hewlett-Packard refer to as an interferometer, which is not correct. It's a polarising beam splitter. And we need some special mirrors, which are called retroreflectors, that displace the beam by 1/2 inch so that the forward beam and the return beam are exactly parallel and exactly displaced by the correct amount. And to do that, you need to use a proper cube corner mirror, which is what's called a retroreflector. Now those sorts of things are available, but I wanted to see that we had a good, reliable 2.5 meg reference signal being produced by that, which tells me all of the electronics in there are working. We've already confirmed that the count electronics are working okay, and even though these signals aren't perfectly clean, that's not too bad. It'll probably still work okay because the input circuitry of the counting electronics in that system actually clean all this up. It's got what's called a Schmitt trigger on each channel, which takes the input and it squares it all up, and it puts it through some logic gating, which outputs perfectly clean signals that the count boards and the registers that were looked at in previous videos are used to count those fringes. So it's actually these things that are being counted. On one counter we're counting the reference channel, and on the other counter we're counting the return beam. And at the moment they're going to be exactly the same, so display is going to keep giving us 0. As soon as we start to shift one of these so it speeds up in any given amount of time, the reference signal will stay the same. The return signal will have changed because it'll be actually moving like we saw the sound waves move before, and that's what the counter counts. And each time one of those interference fringes passes, it knows that you've just crossed 1/4 of a wavelength of light. and that's how it works out how far the distance is. It's actually counting quarter wavelengths each time a fringe passes. They're called interference fringes. Okay? And you can go and study all the physics on that if you like. So at this point, we're all good to go. Thanks for watching.